A lot of smart people have been standing there on the beach, looking out and thinking, the waves, they roll in all the time. What if we could find a way to harvest that energy? And a lot of smart people have tried, but it has not been easy. Most devices historically have not survived the tough storms, or if they did survive, they became large, heavy and costly compared to the amount of power output. We probably need to make wave energy about 10 times more efficient. We are on a mission to power the planet with clean electricity from ocean waves. The challenge for the world to become 100% renewable, going away from our quite severe dependency on fossil fuels that we have in Europe and elsewhere, is to make sure that we can get a consistent mix. A mix of solar PV, on-land wind and wave energy. On the big oceans, such as the Atlantic or the Pacific, you have swell coming into our coastline, which is a very consistent and complementary power profile to wind and solar. Wind is a concentration of the solar heating. Winds are then concentrated into ocean swell. And when that is happening over a process of several days, there's a natural smoothening and storage effect happening. The oceans can work for us as possibly the largest battery on Earth. It's storing the energy from the winds, smoothening the power profile, and then we pick it up on the coastlines as firm, clean power. So the role of wave energy is to fill the gaps. When it's not windy and when it's not sunny, the waves keep coming in, much more consistent. We fill the gaps and you can create a mix that is 24/7 clean. So currently we have one first commercial scale C4 machine deployed, and we're currently manufacturing the next 3 C5 machines, which is going to be the first industrialized version of our wave energy converters. And now we're aiming to have a big degree of simplification from the first machinery. So we have about half as many components. We have half the cost of the machine compared to the C4, and we're now building 3 of them to deploy in Agusadora. What we're seeing here is parts coming in and various subsystems that are being developed by our European suppliers. We're doing final assembly and then dry testing in this big dry test facility here in Stockholm. So here we're looking at a quarter scale model of our composite hull. It's manufactured on the same additive mobile factory technology as the full-scale device, and it's made out of composite. So this is a very sturdy skin. Even though this is a composite technology, we focus on very high level of durability, so you can bump into these devices with vessels without actually making damage to them. We weave up these devices by glass fiber that we add layer by layer in a weaving process. It's a fully automated additive technology. We're now squeezing the manufacturing time to be able to churn out 1 buoy hull every second day, so 48-hour cycle time on this production. It's optimized for doing local production, so if a customer wants a farm with a few hundred of these devices, we bring the mobile manufacturing cell to the customer site. We produce the amount of hulls needed for that project, and then we move the mobile factory cell over to the next customer site. So the whole thing has been optimized with a high degree of automation that allows cost-effective manufacturing locally in Europe and other parts of the developed world. The full-scale version of the C4 device is then 9 meters in diameter and about 100 tons of total materials, including the machinery.
Europe can build. What's missing is her story. For decades we got taught to fear the future, not build it. That's why we are making documentaries about the engineers, scientists and founders building the future here in Europe.
So we're looking at the next generation CorPower C5, about 100 tons of materials, 10 meters diameter. It has a composite hull, the primary structure interacting with the ocean waves. So when the buoy is lifted up and down, it's then pushed down again in the wave trough by the pre-tensioning system, which is the cylinder that you're seeing here. So this makes sure that we can get the same motion up and down, and we can extract power in both directions. The linear motion that is being made up and down is converted into rotation using our patented type of cascade gearboxes. And then we have 2 generators from the automotive industry that then convert that rotation into electricity, and then we feed it through a grid inverter and a step-up transformer that creates grid-compliant power output. And we're having a cable running down one of the rods and then going all the way down to the seabed. And then you connect these CorPower clusters up with a collection hub where the power from the 30 devices in a 10 megawatt CorPower is then collected up, and then we have yet another step-up transformer that turns it into typically 66 kV export that can then be exported out to the online grid, or it can be connected together with offshore wind turbines, and you can combine these wave energy converters with offshore wind turbines and create co-located farms. Each wave energy converter is rated at 330 kilowatts, meaning 3 of them per megawatt. So in a 10 megawatt CorPower, we have 30 wave energy converters. We have 1 collection hub, and that is then the cluster that we call a CorPower. Now we are in the control center here in Stockholm, where we are both running devices in dry testing, but also operating them in the ocean. So on the screens here, we can see some live views from Goçadora in Portugal, where the device is operating. This is the CorPower C4 machine, our first commercial machine. It's an autonomously controlled machine. It does about 100 controlled decisions every second. The devices, they are point absorber, so buoys oscillating up and down and side to side in the ocean. They're anchored to the seabed using what we call a UMAC anchor, embedded a pile about 20 meters into the sand. And then there is a universal link at the seabed, so the whole device is allowed to pivot around the anchor point. The challenge with wave energy has been to have devices that both can survive the big storms and produce a large amount of power compared to the size and the cost. The trick we've been able to add is a storm protection mode. The device puts itself into a detuned protected mode when the waves get too large, and because of that it doesn't react to the waves. We can compare this to pitching the blade of a wind turbine. Every commercial wind turbine is pitching the blade and putting it more horizontally when it's too windy to avoid overloading. That's the kind of function which has been missing in wave energy previously, and we have added it, but instead of pitching the blade and physically changing the geometry of the device, we are changing the stiffness of it. It wants to move, if you say, much faster in frequency than the ocean waves coming in. So we're doing the change in the frequency plane rather than in the physical domain. So it's just letting waves pass by without reacting to them. That's how we can survive the biggest storms. We have proof points here in Portugal. We have had close to 20-meter waves sweeping over the device, and it survived every one of them and is moving about 2 decimeters up and down in a 20-meter wave. So that's the first main inventions that we brought. The second one is the phase control technology. So in regular waves, we then change again the stiffness and make it respond very strongly when the incoming waves. We make it resonant, we can say. When we turn on these 2 negative springs that we call the wave springs, then the device becomes highly responsive to waves. In a 1-meter wave, we typically make the device motion of 3 meters up and down. So we're amplifying the wave motion by the phase response of the device to get a lot more motion, and that is the trick. Storm survival, to make a sturdy, reliable, lightweight device that then, together with phase control, produces a large amount of power. And the combination of this has enabled this jump in about 10x improvement in structural efficiency, how much energy we can generate in a year compared to the amount of machinery that we install in the ocean. Rather than building larger and larger individual machines, we do that by just replicating that Lego piece. And you then get cycles of learning, economies of scale, by doing the same thing over and over. The amount of energy that you can deliver being your revenue versus the amount of materials that you use, the structural efficiency, it's the key thing that dictates how competitive you can make wave energy in large volumes. Thanks to the 10x improvements, we have a clear path to deliver somewhere between 40 and 50 euros per megawatt hour. What we did from the beginning was to start diving into the physics and the hydrodynamics of wave energy. We went around Europe, essentially visiting all the places where most testing had happened. And we met all the key people and asked kind of what's been working, what hasn't been working, what have been the issues. By accident, I got introduced through some patent lawyers with the inventor behind this technology called Stig Lundbeck. He was actually a medical doctor, so he was inspired by the pumping principles of the human heart. The heart has muscles to pump out the blood from the chamber, and then in the return motion, when the chamber refills with blood for a next pumping cycle, there is no muscle to pull it back. Instead, it's hydraulically stored energy between membranes that pull back the heart. His inspiration for wave energy was the same, that we have the wave which is lifting our buoy up, and then on the down motion, we use stored hydraulic pressure inside a pre-tensioning cylinder. That means that we can extract the same amount of power when the buoy is moving up in the wave as it's then moving down in the wave trough. That makes it possible to do very lightweight, high-frequency oscillating machines compared to if you just have a heavy floating structure that is self-balanced by its mass. And the lightweight structure that we had and developed turned out to be a perfect match together with the phase control technology that had been then developed in Trondheim by Jürgen Hals. And Jürgen came with the invention that we have later branded the wave spring, which is a negative spring. The more you go away from the midpoint of it, the more it pushes you away. So the opposite to a regular spring. And in wave energy, it had been known in theory for decades that if you had a component that could do that, that would be kind of the holy grail to get a lot of power out of wave energy. But then all by a sudden, Jürgen had an invention, an idea on how such a negative spring could be realized.
I remember I read during my PhD studies that if we could have a negative spring, that's what we need, but that's not possible to make in reality. But it is.
One of the most rewarding things to do this, I think, it's just that energy you get by working together with really smart, dedicated people, being the team that leads the race globally in wave energy. It's extremely cool to do it. The fun of just doing things that you're truly passionate about is just beating anything else. Work and put your efforts into things that really make this a better place. Wave energy is in a really unique position right now. After 15 years of demonstration, technology is proven. We're surviving the biggest storms, we're producing the amount of power expected. We will be ready to start deploying the first 100 megawatt plus type farms. Wave energy by 2040 to 2050 could be the third largest energy supply in Europe. I mean, globally, it is the largest untapped source of clean energy that we have out there. And finally, now we have a technology to start extracting that power and make use of it. So our vision in CorPower is to really bring wave energy to a large-scale mainstream energy source. We hope to be able to make wave energy one of the largest sources of clean energy on Earth. We can build out in a very modular, rapid fashion. There's lots of research going on in fusion as well, and I think big developments are being made. The difference here is that this is now in 2026, a proven technology that we're scaling into commercial farms.